Thanks for being here, everyone, in person and online. And thanks to the organizer for putting this wonderful program together. I've really enjoyed the last few days here and the wonderful campus. So thank you for that. Yeah. My name is Felix. I'm based at Trinity College Dublin, which is in Ireland. Ireland is that small country in the Atlantic Ocean, which keeps the rain and wind away from Great Britain. I'm going to talk about parameter estimation in the presence of temporal correlations. And let's see. So we're thinking here about open quantum systems. I'm going to give a little bit of a more general bit first, but this is a good way to start from. If we have an open quantum system and we're a little bit operationalist-minded, we might think of looking at the system via the outputs that we can detect of it, right? So we're not looking inside the cavity, we're looking what comes out of the cavity. And that's really, if we're passively just observing, that's all we've got to go on. And we want to estimate something about what's inside the system based on this measurement record. Yeah? And so if we're not applying any control or anything like this based on what we observe, this is effectively a classical estimation challenge. Yeah? So we might want to infer a temperature or magnetic field or something like this, yeah? Based on a measurement record like this here. Yeah? And the question is then, what do we do if these are IID samples? If every output is independently sampled from a probability distribution, which is IID, this is fairly straightforward, but of course this is not typically the case. And what happens when there are temporal correlations? Yeah? So here's a artist impression of a very simple open quantum system, a three-level system up here, which can emit along emit or absorb along 4 channels, and we might get a record like this. Again, this is an artist impression out, and how we would describe this record is by giving labels to the type of emission that we see. We call this a channel, so these are these Ks, and then the elapsed times between the emissions. Yeah, so these are not total times in this talk, doesn't really matter, but here there are periods between jumps. Yeah? And the question is, how precisely can we estimate something based on this information? Before I go into the open quantum systems part, I want to talk about, to give a quick overview, correlated estimation theory in a little bit of a broader sense. This is where we started from working on this, before then going into the quantum jump unraveling, which you're all familiar with by now. And then 2 particular cases of estimation that we can look at. There's a sort of fairly simple case, which we refer to as renewal processes, where the entire thing becomes analytically tractable, but which unfortunately doesn't happen to be the case that we expect to encounter more often, or it's the interesting part. So we'll then go to non-renewal processes, processes for which this renewal property doesn't hold, and where we have to deal with the problem numerically. Yeah, so this is the overview. So to quick background on estimation theory. So what we're interested in is we've got some probability distribution which encodes the parameter, yeah, that we're interested, or it could be a bunch of parameters. Notationally, I've indicated here theta as the parameter. You can think of this, if you're coming to this for the first time, as a single thing like a temperature. If you're more comfortable with this, you can also think for most of the talk, you can think of this as a vector of a bunch of parameters. This is just on purpose to keep it notationally simple. There are some differences that come into the picture where there are multiple parameters. Yeah? And so what we do is we sample from this, and then we try to make an estimator, right? A sample mean or something like this to infer the value that we're interested in. And we'll call this estimator theta hat. And so we're hoping that as we keep on measuring, that we get some good enough precision on the result. And the main sort of bound that applies to this is something called the Cramer-Rao bound, which you're probably familiar with or have heard of before. It bounds the mean squared error, the expected variance, by 1 over a quantity called the Fisher information, which I'm indicating here to correlate a finite length, correlated set of potentially correlated set of random variables by 1 to n, so just so we're keeping in mind that in principle we're looking at correlated things. In principle, n could become very large. Yeah? This guy Rao here, by the way, was born in this part of the world. He is from what's now Karnataka, from close to Hampi. So there's a little local connection. Kramer was Swedish, I think. Good. So let's look at this. The Fisher information looks like this. This looks a little bit complicated, but it's essentially a expectation of this derivative with respect to the parameter of the log probability, which has the parameter in it, and that entire thing squared, which can also, under fairly straightforward regularity conditions, be written in terms of a second derivative, and then a minus sign pops up in front. Yeah? And so you can think of this really as an average dependency of the parameter being encoded in this probability distribution, yeah, via the derivative. So this is fairly intuitive, that this is the type of quantity that would give us an estimate or a bound on how closely we can approximate something. We can look at, for a start, we can look at the case where all of these random variables are IID, that's independent and identically distributed, in which case you can very easily see that the probability distribution factorizes, and this just becomes a product of single Fisher informations of the marginals. Yeah? So this gives a linear scaling. I should say, I didn't mention this before, this entire bound applies to the case of unbiased estimators. Once we allow for biased estimators, this is not meaningful anymore. Yeah? But so what we get here is a super straightforward linear scaling of the Fisher information with n, where n is the number of random variables. Yeah? And as a teaser, this is what we expect to hold generally also in everything that I'm going to talk about. But what's going to change is the exact quantity, what is here f1, with which it scales. Yeah? The scaling will remain linear, and we'll see this, but this quantity here will change. As a quick diversion, we can do this. I said we can also think of multiple parameters. This is not going to be super important for this talk, but just to mention this, what we would do is we would, instead of a single Fisher information, we would write something called a Fisher information matrix, where we take derivatives, the product of these derivatives here, with respect to two different parameters, and they make that element of the matrix. Yeah? And so you can see that on the diagonal of this matrix, you get what we've had before for a single parameter. Yeah? And then what this bounds, the Kramer-Rao bound, then becomes a matrix inequality with respect to this covariance matrix up here, which you can read. So this is the inverse of this matrix up here. So you can read this as this difference being a positive semi-definite matrix. That's what the Kramer-Rao bound says. I don't want to go too deeply into this. For all practical purposes, we can think of the theta as a single parameter for the time being. Second, we're interested in now what happens when there are correlations. Yeah? So when the variables are not IID anymore, which is of course nice if that's the case, but it's not always what we want to have. If we can, what you do in quantum metrology, if you can get correlations into there, we'll see that you might actually increase your estimation performance. So even if you get to engineer your system, you might want there to be correlation. So this is a relevant case to look at. Yeah? And so what one can do purely mathematically is to define a conditional Fisher information, yeah? Which has these conditional probabilities in there. And this is just a mathematical equality or a mathematical definition, right? You can think of this, there's a whole game that you can play. I can point you to this first reference down here of trying to treat the Fisher information and define a bunch of things that you would with an information entropy. Yeah? You can make a mutual Fisher information, etc. And some of these things become a little bit unclear because of the two ways of defining it with a first or second derivative. The only element that we're going to use here is this conditional Fisher information. And what we get from it, the point of doing this is that we can now write so this is the total Fisher information here with two variables in it. The chain rule which we get for this is that the conditional Fisher information is the difference between the total Fisher information and the local Fisher information on the marginal on one side. Yeah? And we can use this to unravel for this entire string for 1 to n, to unravel the entire Fisher information in terms of these sums. Yeah? This is per se not super useful. It's just something that happens to be correct. We'll see we'll see why this becomes useful when there's limited correlation length in the process, right? This is a rewriting which basically has more or less the same things in it. But so we would start from the Fisher information on the first marginal, then go to the condition on the first marginal, on the second one, etc., and keep on conditioning, but we have to keep on conditioning on everything in principle, yeah? Which is why this is not per se useful, it's just something that is there, yeah? And what we hope for in this, generally in this correlated picture is that as we take more and more measurement records into account, our error of the estimation goes down, yeah? And as I've already said, this will be linear again. The question is with what quantity. So let me introduce something here, another important bit. We can think now of stationary processes and make an assumption which basically amounts to there not being an explicit time dependence. Yeah, so stationarity means that the probability distribution is shift invariant, which is similar to saying there's no periodicity to it and there isn't an explicit time dependence that at some time t suddenly it behaves differently, or at all times t it does something different. Yeah? The effect of this is that what was IID before now becomes not independent, but still identically distributed due to the shift invariance. Yeah? And that's a nice type of correlation to look at. And what we can invoke then is a quantity called the Markov order, which is used a lot in hidden Markov models, which says we can find the shortest length at which we conditioned the conditional Fisher information on all of this past, which I'm taking to minus infinity here. For just this probability distribution, the Markov order is the shortest length at which we can truncate the conditionals. Yeah? So you might only look at 2 or 3 points of past emissions, and you don't gain anything extra by looking further into the past. Yeah? So what we refer to as a Markovian system usually in physics is one which has a Markov order 1, where the current state matters for the future, but nothing before then. If you know the current state, you don't need to know anything previous. If you didn't know the current state, something previous might still help you. So there are longer correlations, but the conditionals get truncated. Yeah? So that gives us a Markov chain, and if it's completely IID, that would correspond to a Markov order of 0. And so what we can do now is we can show that the Fisher information, just plugging this into the chain rule directly, we can truncate it here at the Markov order, and then we just get n minus m times that contribution. And if m becomes very large compared to the Markov order itself, it's basically this becomes the leading term. In principle, we don't have a guarantee how large this conditional bit is compared to that bit. It could be that there's a very large amount of information in the first few bits, but as n becomes, as asymptotically, it's this bit which determines how well we scale in the estimation. Yeah? So this is what I've promised before. Ultimately, what we get is the Kramer-Rao bound is approximately for large n, 1 over n, but now with this new quantity, which is this thing over here. Yeah? So it's still linear, but it has a different slope now, which could be in principle smaller or larger, and we'll see that. So this is just comparing it again to the IID case. Same thing with different slope. So before I go to the open quantum systems, what we did first is a very simple example that comes to mind is thermometry on a spin chain, where you think of scanning through the spin chain. This is sort of neat because there's some thermodynamic interpretations to doing this. So as it turns out, the Fisher information, this is think of a spin chain which is in a thermal state, and you're trying to estimate the temperature. So it turns out the Fisher information there corresponds to the heat capacity over T squared, where T is the temperature. And the heat capacity and the specific heat capacity are defined as here. So in the large N limit, we get this the specific heat capacity scaled by this T squared as exactly this bit of the Markov order that we just identified, of the Fisher information that we just identified. Yeah? So let's look at this. Let's take an Ising Hamiltonian, which is characterized by these two parameters, B and J, and what we can look at just to see, to compare this against the hypothetical case where we had the same marginals, but they were independent. So there weren't any correlations. We can look at this quantity. where this is a Markov order 1, so this is as long as we need to look at for the Fisher information. The one-side hypothetical version times 2 times the two-side actual Fisher information, compared to the two-side actual Fisher information. And so this is what you get. You can see the scale over here. So at where this is equal to 1, down here in the bluish range, these are roughly equal, and when it's larger than that, when it gets a little bit more green or even red, white is when it's off the scale, it's even larger. We have an advantage, basically. We can think of the correlations as giving us an advantage in this case, which is sort of naturally given to us. We haven't engineered this. We might alternatively also exploit the same type of thing to engineer a probe or something like this, but we're interested here in looking at something where we're naturally confronted with the correlations, yeah? And so you can see as a rule of thumb, you can find counterexamples to this, but as a rule of thumb, what we find is that if the system is positively correlated from side to side, there isn't a benefit to the correlations, and when it's anti-correlated, as in the anti-ferromagnetic phase down here, there's a benefit to the correlations. Again, this is a rule of thumb just based on some of these examples and not universal. But okay, so this is the first message to take away from this. The IID hypothesis doesn't usually hold, and we'll see that this more generally, but we're interested in cases where this doesn't hold. But for finite Markov order, we can still get a linear precision in the Fisher information, but with a new quantity, with this conditional Fisher information. And then correlations can be helpful or detrimental. It depends on the correlations and the nature of the probability distribution. So good, let's go directly to the open quantum systems. And you've seen this already, so let's go into the jump unraveling. What we're interested in is a master equation. This is a Lindblad equation. Here, you're all well familiar with this. It has a bunch of what we call channels here, which correspond to the dissipative part, and we label them by K. And what you can think of as an individual trajectory, I'll show this more closely in a moment, is as starting from some state, and then there's some time of a no-jump evolution. We don't see anything. A jump occurs instantaneously in this picture, no-jump evolution, etc. And this makes our measurement record. So the taus and the k's make the measurement record. Yeah. And so how would we write this down? I'm writing here curly letters as super operators. Yeah. So they act on from both sides, and I'm just writing them as here. So this is the jump effect. Then the no-jump super operator looks like this. This is the entire Lindbladian minus the sum of these jump effects, at least for those channels that we're actually observing. That might be a subset of all of the channels. And the no-jump evolution looks like this. So it looks like a evolution with this no-jump super operator. Yeah. And so what we get is then a stochastic master equation, and now we can look at the jump unraveling and try to do our estimation on this basis. And we do this by looking at the measurement record, which we've just already seen, which looks like this. The probability of it is the trace of this successive application of the jumps and the no-jump evolutions. The question is, what's the Fisher information in this? Yeah? We can do this in principle. I should highlight this up front. There's two ways that we could go about this now. Yeah? And we could look at, in particular, two examples. So one is, we look at what I've already identified as the measurement record, channel labels and elapsed times between jumps. And we call this the measurement record and try to do our estimation based on this. We could also create a record which corresponds of time discretized record, which has a bunch of zeros where there is no jump, and then it has a symbol of the corresponding channel in the interval in which this happens. Yeah? In principle, this contains the same amount of information, but numerically these are very different, and also for purposes of estimation. So we're going to stick to the top one for the most part, but I'll get back to the bottom, which we call the TF ensemble down here at the very end. So now let's look at some processes in the jump unraveling. The simplemost case, which is not ultimately going to be the most interesting case, but we can do a lot here. So let's start with the case which we call multi-channel renewal processes. So a renewal process is something which, under an emission in this language, it resets to a specific state. Here we allow reset to a few states where the state depends on the channel. So if we've observed an emission, we know with certainty where the state is. And you can see that actually these sigmas, the states to which it resets, turn out to be pure in this case. And we assume that we observe all of the emissions here. Yeah? So the simplest example that we can think of is a qubit which has some Hamiltonian that applies to it, and then it can either absorb or emit a photon, right? That's the most straightforward thing that we can do, and we can think of a temperature being encoded into the probabilities of this emitting or absorbing. Yeah? And so what we get here, what we see now is that it turns out in this ensemble that we have of the jump times and the jump channels, this turns out to be a Markov order 1 process, which is now very useful because the entire probability distribution that we had before, the object up here, just it boils down into these successive smaller parts, which is what we call the waiting time distribution down here. So this is just the trace of the system evolved from whatever state it started in, which due to this being renewal, we know for certain then where it is. It evolves without a jump for whatever time tau, and then it jumps into the channel K. Yeah? So this gives us something called the waiting time distribution, which is normalized to 1 if you integrate over tau and you sum up over K. Yeah? This distribution here. And so here you can see, just for an illustration, the waiting time distributions plotted for this process. So for instance, if you've seen a jump in this channel, so you've seen an emission, you have to wait for a while until the probability becomes relevant to see another emission, because there isn't anything left. The Hamiltonian has to do its work along the way. Yeah. Alternatively, if you look at the orange curve, for instance, if you've just seen an absorption, that makes it a lot more probable to quickly emit again. Yeah, and it depends on the exact parameters. But so this is the type of thing you're thinking of. And now we can look, since this is a Markov order 1 process, we can directly apply everything that we know about. This is the simplest case in a way, right? So this entire Markov order, we can see here in this scenario, it turns out the interesting cases are either the Markov order is 1 or it's infinite, basically. So this is the Markov order 1 case, and we directly have the scaling of the Fisher information here in terms of the waiting time distributions. This has in it the steady state. Klaus commented on this earlier already during his lecture. So there is some, I put an approximate sign here. This depends in principle on the initial state. So as it jumps, we know what state it's jumped to. We can compute it exactly, but it carries some record of the initial uncertainty of this guy up here in principle. Yeah, that's not a problem because we go for longer times, and then the Kramer-Rao bound scales linearly again with this quantity down here. Good. What we can do in this case is we can apply the chain rule again, and now to find a separate Fisher information for the channels that it's jumped into. There's some information that we gain from that. It has a red or a green photon come out of the cavity, and a second amount of information which is due to the time at which it's come out. You can think of this for dumbing down your simplifying your measurement record to get rid of the times and just record a succession of channels, for instance. Yeah? And so this becomes additive in this case, as we can show, where the channel part doesn't depend on the time anymore, whereas the waiting time distribution here for just the times gets rid of the channels in which we've jumped into. Yeah. So we have an additive bit, and we can look at this again for our example from earlier. So here you can think of this as there's a data processing inequality that applies to the Fisher information. So you can think of this as data processing, which is applied after your record is created. You throw the times away and you only look at the channels. Yeah. And how much information do you lose by not looking at the times anymore? You could do the opposite as well. Yeah. And so this is plotted here. This is the Fisher information divided by n for thermometry. So we're trying to estimate the temperature encoded in these thermal populations here. And you can see how this is the orange curve is the information in the channel only, whereas the blue curve is the full information. And here on the right, you can see the proportion of the channel Fisher information versus the overall Fisher information. Yeah, so this is very high at the beginning. At the beginning, we don't learn much from the time, but we learn a lot from the channel. And as time goes on, we learn more from the times as well. Yeah? Good. That's it for renewal process. This is a fairly straightforward case and not the most interesting bit per se, but we can look at everything analytically. Yeah? Now a question that directly arises is what happens if we don't look at all the jump channels? The renewal condition is out of the window, generally speaking, and so this motivates directly even from this that we should look at the non-renewal case. And this gets a little bit more interesting. So again, we have this probability of computing, of seeing a particular trajectory, but now the question is how do we compute the Fisher information in this case? We haven't got this unraveling breaking down at some level of the Markov order, and how do we perform the estimation? So the intuition that we should have here is that the Fisher information still behaves linearly in time, but at this point we can't compute the quantity with respect to which it behaves linearly. But we could hope to get the slope numerically. Yeah? And so there are a couple of tricks that we can use. I'm not sure if Klaus might tell you these a little bit more didactically and in more detail tomorrow. But let me give the gist of it here. We can employ a tool called the monitoring operator, which is defined like this. So it's the derivative of the unnormalized state being this thing up here with respect to the parameter, and then divided by the probability by the trace of this unnormalized state. Yeah? So the sort of normalized version of the derivative. Yeah? And then it turns out, if you compute this, I won't go through it now, that the expectation value of the square of the trace of this operator, yeah, corresponds exactly to the Fisher information. This is, for now, this is a rewriting basically, but it turns out that this is numerically useful as we try to compute the Fisher information. Yeah? It's also useful for the maximum likelihood estimation itself, which is the way in which we try to estimate the parameter, because as it turns out, the point where we're finding the correct parameter is the point where this trace vanishes. So we're looking for the minimum candidate parameter of this trace or of the square of it. And that'll give us the optimum in a maximum likelihood sense. Yeah? So I want to spend the last bit now of the main part of the talk on explaining what we can do here numerically, having this measuring operator in the back of the mind. Yeah? And what we're going to do is this. We're going to generate the waiting time distribution for specific present state. Then we'll sample from it, and we'll use, so that sample will tell us the time at which we expect, or the sample tells us how long to evolve the state until a jump occurs, irrespective of the type of jump so far. After that, we'll generate the distribution of what's actually the jump, and we sample from this, yeah, at this time which we've sampled from up here. And then lastly, we evolve the state and the measuring operator forwards with the jump as well. And then we keep on doing this. Yeah? This is the sort of numerical algorithm that we're going to use. And the advantage of it is that we can pre-compute some of the quantities in this and store them, which means this works well for small systems. Afterwards, we run out of storage. But as long as we can store these quantities, we can compute this efficiently. And let me show you how this works. So the first part is we generate this waiting time distributions at the current state. So this is what we want to generate is this thing. Yeah? And it's defined like here, where now I've summed up over all of the observed channels. Keep in mind, these are super operators and the no jump operator here as well. Yeah, so these act on the state which we've currently seen, and then it gives us a distribution where we can sample this tau from, yeah, with this probability. So we sample from it, and then we take this time. So this Tj is the tau that we've just sampled. It's a T to indicate that it's the sampled value at this time, and we evolve the state forward. We renormalize it again. The renormalizing is convenient because we don't have to keep track of these vanishingly small probabilities. Yeah? Now we want to generate the distribution over the jumps. So how do we do this? It's just given directly as this here. So this is a specific jump normalized by the probabilities of any jump happening, and we can pick from this. Yeah? So the K is what we pick. So now we can take this not any more normalized state, rho bar, and we can evolve this forward, apply the jump that we've just selected according to the new probability distribution for the jumps, and the overall of, and now we get the final state. And we can do the entire thing again. We also need to deal with the measurement operator. We can think of the sort of joint effect of both of these parts, the node jump and the jump effect, as this effect down here. This is a Krauss operator. We've seen the description in terms of Krauss operators a few times already. You can think of this as a quantum instrument, basically, made up by these Krauss operators, where you can see that these parts don't depend on the current state. So this is something we can compute in advance. Yeah? It depends on the time. So what we'll do is we'll pick a bunch of these times, but they don't need to be closely as fine-grained as in the time discretized case to get a precise outcome. So we pick a bunch of these times and make a bunch of these operators for these times, and then we sample and run through this process. Yeah? The other operator, so and with this we can compute the next state. Yeah? We also need to forward evolve the measurement operator itself, so we can compute the Fisher information and do the maximum likelihood estimation. So this part we've already computed. Also down here, these Krauss operators. The additional bit that we need to compute is the derivative. Again, this thing doesn't depend on t. It doesn't depend on the state. So this is also something that we can store in advance. Yeah, for this selection of t's that we've made. So that's where the sort of numerical efficiency comes from. But you can also see that this explodes if the system becomes very large. So it's a neat thing for this corner. If you're interested in this corner of simulation where there isn't so many jumps, this is where the advantage over the time discretized, where the jumps are rare. That's where the advantage over the time discretized case comes from. And where the system isn't too large, or your RAM is large enough anyway, so you can store all of these effects. Yeah? Good. And so to summarize this again, we've pre-computed the relevant bits now. And this lets us simulate all of these trajectories fairly efficiently in this case. Yeah? Here's an example of what we can do with this. These are two coupled qubits with a single emission channel. And you can see here the expectation value of the population in either of the qubits. The A1 is on the left, that's the blue curve. And the dashed curve is the one on the right. And you can see that when a jump happens on the right, we can directly reset this, whereas this doesn't happen on the left because we're not looking at it directly. Yeah? And so what we obtain is, again, a linear scaling of the Fisher information, but now we don't have a analytical expression for it. It's just a numerical. This is what we would always expect. We can make a pathological process where memory is infinitely strong at infinite times, but this means that we have an exponentially exploding memory, so this never actually happens. So in practice, we always expect it to look like this in any real world system. Yeah, just we compute this numerically, and then we can look at the Fisher information over here as well in the time ensemble. And let me just jump back to this to say how we do this. So we can look at this Fisher information rate now as a function of time for a time increment, and it turns out that this is exactly encoded in the stochastic current of the individual jump channels down here. Yeah? And the maybe interesting bit is that it's just the sum of these. There is no sort of, they're not talking to each other along the way. The Fisher information, the increment at this order is only in the sum of these individual Fisher information effects. That's what I wanted to say about the non-renewal processes. So in general, we expect the Markov order to be infinite in this case, which means all of our neat tricks of using the chain rule and computing the Fisher information for finite length conditionals are out of the window. But we can numerically use the monitoring operator and this Gillespie-Fisher algorithm to track this. In particular, this works particularly well when there are few jumps or rare jumps and the system isn't too large, let's say. Yeah? So I should acknowledge here, these are the references, the first three in particular, the correlated estimation theories in the first one. The second one has this Gillespie algorithm in it, independent of the estimation part. And the last one is the quantum jump unraveling estimation. And you can see here, they all share a first author, which is Marco Radaelli up here, who has me point out that he also has a poster on the same topic out here, and we'll be talking about a more recent thing that on hypothesis testing that comes from this on the 4th of February, which is next week, Tuesday, in the afternoon. I should give me one more minute. I should thank my collaborators here, Joe Smiga and Gabriel Landi at the University of Rochester were involved in all of this, and Kavan Modi, who's currently in Melbourne at Monash University, has also contributed to it. And to abuse my standing here in front of you, let me take 1 minute to quickly also advertise another conference before we get to question, which is taking place in Singapore in the summer. I have the pleasure of leading the program committee for this, and there are a few other members of the program committee also here in the room. If you're enjoying this conference here a lot and you're also interested in thermodynamics, here's an option. You can take a photo of it if you want, or go to this website. Abstracts are accepted until 17th of February. Then we'll jump back to here, and thank you.
Hi, Felix. Thank you very much for the talk. So could I just ask, if I just have a canonical driven dissipative system, then what Markov order should I expect of it? Infinity?
So this Markov order applies when the system is stationary. The process that governs it is stationary. Yeah. So if you have some generic type of driving, that's not the case.
Okay.
So, but this would correspond to a logic of there being infinite Markov order.
And just one more question. So there is this linear scaling, and I presume, and I just wanted you to react to this. I presume that the reason that you're getting linear scaling is because you fix your measurements in the beginning. So you choose what you want to measure, and that's the reason that you don't get the quantum Fisher information scaling of n squared.
So that's a very good question. Thank you. This is basically completely classical, and the reason for that is that we are confining ourselves to be passive observers in this thing, right? And this is why we get the scaling. You might take the opposite approach, which is very common and sensible, to say, how can I engineer this thing such that I learn the most about the parameter? And then you could do quantum metrology, etc. But this doesn't apply if you've picked the unraveling, the jump unraveling here, for instance, or more generally, if you've picked what you observe, and that's a specific measurement that happens, you don't get that option.
Could I just ask one last one? Is there any advantage over, do you anticipate from this kind of study that there is any advantage at looking at the trajectory as opposed to looking at the average dynamics? Because you could also just say that I have a parameter that I want to estimate, and I just look at the average dynamics. And would there ever be some kind of advantage in looking at one and not the other?
I'm not sure what you mean by average dynamics. The good question.
Just the Lindblad as opposed to the DW.
Yeah, so you can get the average dynamic by averaging over the trajectories, right? So you can think of this in principle as a post-processing, I think, which will reduce your Fisher information. This probably, yeah.
That's a fair point. Yeah. Thanks.
Thank you for a really nice talk. I actually have two questions, but maybe the most burning one. In your icing chain, there were some red dots in the antiferromagnetic order phase. There must be interesting physics behind those red dots.
Yes. Where was it here? So there's a lot of interesting physics in this. Let's say thank you. One thing is one could look at longer correlations and all of these things, and they would map onto the Markov order. The question is why does this behave the way it does, and why is there this line along the way, is what you're asking. The sort of mathematical reason for this is, before getting to the physics, is that maybe this is not the optimal quantity to look at. It's what we picked and what we started with. This is where the plot came from. Dividing this in this way is maybe not the optimal way of seeing the difference, because you can't tell apart cases where this just happens to vanish on a single site and it blows up, and cases where this becomes very large and this doesn't vanish. So there might be a more nuanced way of looking at this. And so as I remember this, but Marco, you can correct me if I'm getting this wrong, this is a sort of frustration effect. The antiferromagnetic phase has a ground state which is either like this or like this, and then repeated, right? Either up, down, or down, up, and then repeated. And I think this is the point where it wants to choose to go into the all down ground state. And at this point, this thing vanishes. So you don't learn much from a single marginal. Again, this is a hypothetical case. This is not, you're not actually learning this. You shouldn't think of this being a physical thing to look at, because if you were to make a new Kramer-Rao bound and an artificial one with this quantity here, it would give you some linear scaling, but the bound might be lower or higher than the actual bound. It wouldn't be a meaningful thing, right? So this is a very hypothetical comparator, just to get a sense for what do these correlations do in a scenario where we assume them to be sort of naturally given to us, not engineered. Yeah.
So a technical question. You had this Fisher rate that you showed, and it was a nice and beautiful expression. It contained a row inside of it, and there was a C on it, so I assume it's a conditional row. So does that mean you calculate that quantity, but then you have to average all the different possible row C's in this lower line expression?
Yeah.
Yeah. So it's not a steady state density matrix you put there. You actually still have to do the simulation of the record to sample those row C's.
This is a good question. I would.
Yes. Okay, good. Thanks.
Okay.
Hi. Thanks for the nice talk, Felix. Could you go back a slide? Yeah, in this Gillespie-Fisher algorithm, is gamma the rate of jumps in figure D?
Yeah.
Am I interpreting right that the more the system encodes more information when gamma is less? Is that why the rate of Fisher information is decreasing as you learn more about gamma?
So what we're estimating here, this is a good question. So what we're estimating, if I don't misremember, this is actually a coupling parameter on the I think on the left qubit. So the gamma this will have an influence on how much information you're gathering from the gamma, but we're not estimating the gamma.
Sure. I mean, the more we learn about, more the jump rate is, the less we learn about it. Is that what figure D is?
On this plot over here, this would tell you that you learn more that the higher the jump rate is, and you're wondering if it should be the other way around. I don't have a good intuition now for this on this spot. Yeah. Yeah. Yeah, I guess this is, I think the reason for this is that this is a Fisher information now per unit time, basically. So if you're getting more jumps, you're getting more information in the channels, even if maybe you're getting less information in the timing of the jumps. This is not, so the way that this is plotted is not per jump, right? At this thing, in this direction, is not per the information per jump, but the information per time. So if you increase this, you're getting more jumps per time. Would be intuitively how I would read it, yeah.